Hello everyone, and welcome to the presentation about stochastic tile-based lighting. I'm Jarkko Lempiäinen, and I work as a principal graphic engineer at HypeHype. Over the past 25 years, I have focused mainly on developing AAA rendering technology at companies like Ubisoft, Unity, and Treyarch. I joined HypeHype about a year ago, where we are building a user-generated content platform that runs on everything from $99 budget phones to high-end PCs. Currently, HypeHype has about 500,000 games created by our users, which anyone can play or remix for their liking. HypeHype's goal is to make game creation easy and fun for everyone, including casual users with no technical background. This has big implications on the technology we develop because it just has to work with minimal technical skills while having a good quality and high performance across all the devices. We are building intuitive creation tools that run even on mobile devices and are integrating AI into the workflow to make the barrier to entry even lower. When I joined HypeHype, the engine supported only shadowed sunlight, and to boost the visual quality of the games, I started to implement a local lighting solution. In this talk, I will take you through the stochastic lighting algorithm that we developed to run even on budget mobile phones. I will cover the motivation behind it, implementation details, and the result we achieved. To support local lighting on mobile phones, we need to deal with some unique constraints that significantly influence the lighting algorithm design. One of the most critical limitations is the memory bandwidth, which is very constrained on mobile, especially in the low end. $99 budget phones today have around 15 GB per second of peak bandwidth and around 250 gigaflops of ALU power, which is about the same as Xbox 360 and PS3 released 20 years ago. Even high-end phones peak only at around 85 GB per second. For comparison, Xbox Series X and PS5 Pro have over 500 GB per second of bandwidth and respectively 12 and 17 teraflops of ALU power. Unlike PCs and consoles, mobile devices are passively cooled, so bandwidth-heavy operations quickly translate to heat and throttling. To put things in perspective, moving just a byte of data between CPU and DRAM consumes 100 times more power than a simple ALU operation. Mobile GPUs rely largely on tile-based rendering to conserve bandwidth. In this architecture, the frame is split to tiles and rendered tile by tile into small but fast on-chip memory. Once all triangles for tile are rasterized, the tile rendered target data is written out to main memory, often using lossless frame buffer compression to further reduce the memory transfer costs. To take advantage of this, rendering algorithms must be written with pixel shaders instead of compute shaders, and the number of render passes should be minimized to reduce DRAM round trips. To optimize the ALU usage, algorithms should be written from ground up to work with FP16, since mobile devices have widely adopted double-rate FP16 pipelines. Besides this, there are the common GPU optimizations, like minimizing branch divergence and optimizing vGPU usage. From the user side, our platform is designed for casual creators, which poses some extra challenges for lighting. We can't expect our creators to understand performance trade-offs or tweak lighting parameters for different hardware. Lighting consoles must also be intuitive and robust to make lighting the scenes simple and fun for our creators. And we must deliver consistent results whether the game is created on high-end PC or phone and played on a budget Android device. The performance and consistency must hold up, or it could lead to gameplay breaking issues. We must also prepare that lights may be randomly spawned and moved. For example, every pink orb here is a light created whenever an enemy dies. We can't afford large frame rate drops or visually disturbing artifacts because of unpredictable light clumping. Or our creators might just decide to add 50 shadowed lights to a room, because why not? The creators git pass scenes from our asset library prefabs that can include lights and quickly populate game worlds with a large number of lights. To explore existing lighting solutions, we consider tile-deferred lighting used by many modern renderers. The benefit of this solution is local memory access and wave-coherent lighting evaluation, which is good for high GPU performance. However, it scales only linearly with the number of lights per tile and assumes that artists light scenes carefully, limiting their region of influence to keep the performance in check. Even in quite simple scenes, the light count per tile can become high, especially at object silhouettes as highlighted here. When dynamic lights are added to the mix, the lighting cost can be very unpredictable, causing performance issues especially on weaker devices. Some engines limit the number of lights per tile, but exceeding this limit results in flickering tile artifacts. The light culling for the tiles is also quite costly, especially when done precisely with exact tile frustum checks. We had also looked at Rister by Pitoli et al. For a stochastic lighting solution. The benefit of stochastic lighting is the fixed cost regardless of the scene lighting complexity, at the expense of some added noise. You can have many lights influencing a single pixel without blowing the lighting budget, like in this night shot I just took here in Vancouver. Rister performs light sampling per pixel, and in addition to uniform scene light sampling, it resamples lights from the previous frame local pixel neighborhood. The uniform sampling accesses scene lights randomly, which is quite cache unfriendly and increases the memory bandwidth usage. Because the result from the uniform sampling is very noisy, Rister performs another spatiotemporal resampling step from the history buffer, which is another cache unfriendly and bandwidth heavy operation. Doing such bandwidth intensive sampling per pixel makes this algorithm quite expensive on mobile. Also because of the per pixel sampling, light data and types can vary randomly per pixel. This causes incoherent light data loss and diverging code execution paths during lighting evaluation, which hurts performance. We weren't aware of any existing lighting solution that matched our needs and were designed low-end mobile in mind. This led us to develop our stochastic tile-based lighting algorithm tailored specifically to work within the mobile limits. The stochastic tile-based lighting algorithm performs light sampling per tile rather than per pixel. This means that for each tile, we store a single set of light samples shared across all its pixels, significantly reducing memory usage, bandwidth, and wave divergence during lighting evaluation. Much like traditional tile deferred lighting, this allows threads in a GPU wave to take the same execution path and benefits from coherent data loads. We also designed the algorithm so that all the passes can be implemented efficiently with pixel shaders to benefit from tile-based rendering architecture and frame buffer compression on mobile. That said, compute shader implementations can further improve performance depending on the hardware architecture. To minimize noise and denoising cost, we wanted the light sampling to be guided by a high-quality important function that closely approximates the influence of each light to a tile. For instance, if a tile is fully in shadow from a light, that light should ideally not be picked for a lighting evaluation. However, computing a precise PDF for every tile and light in the scene would be far too expensive, so we developed a two-stage sampling process using Stratified Reservoir Sampling. The algorithm starts on the CPU side with the camera field of view culling of the scene lights. The list of culled lights is passed to GPU for the first big tile sampling stage, where the screen is divided into larger tiles. For each big tile, we use Stratified Reservoir Sampling to select a subset of lights based on a simple low-cost PDF that roughly approximates lights importance for the tile region. Then in the small tile resampling stage, we resample few lights for small tiles by performing another round of SRS from corresponding big tile reservoirs. This time we use a higher quality PDF that includes more accurate light visibility and PRDF terms. The light sampling is followed by deferred shadow pass, where we evaluate shadow terms for small tile light samples and for all the tile pixels. The shadow evaluation is decoupled from the lighting shader to optimize performance. Finally, during lighting pass, we read light samples and shadow terms for each pixel, evaluate the PRDF, and apply proper light weighting for the final lighting result. The light sampling starts by sampling a subset of scene lights per big tile to reduce the number of candidates considered during the subsequent small tile resampling stage. Each big tile covers a 128 x 128 pixel region of the image, as shown with the checkerboard pattern. For every big tile, we stochastically select 16 distinct lights from the scene and write them into the tile's reservoir. For the sampling, we use Stratified Reservoir Sampling. SRS is without replacement sampling algorithm that ensures we don't have light duplicates in the big tile reservoirs and that we use the reservoir space efficiently, which is important to maintain a diverse and representative set of lights for each big tile. SRS can also be implemented efficiently with pixel shaders because each reservoir slot is independently sampled. Each resulting light sample is stored in a 32-bit format as shown in the image. For pixel shader implementation, the big tile sampling shader is evaluated for each big tile reservoir slot that exports the 32-bit light sample to the render target. The light index refers to the buffer containing the camera FOV colored lights. The light weight is the inverse of the PDF. The reservoir samples are stored in 4x4 pixel regions in the render target for improved cache coherence. For example, 1080p frame buffer requires tiny 60x36 pixel render target for the storage. To compute the PDF for the big tile sampling, we start by fetching the depth bounds of the tile from hierarchical min-max depth buffer that was generated after the gbuffer pass. For 128 pixel big tiles, we use lot 6 of the min-max depth buffer, which has the same pixel footprint as the big tile. Next, we construct the tile central line segment between the tile depth bounds shown red in the image. During SRS, we use the same PDF for all the light types. For this, we evaluate OmniLight's color illuminance at the nearest point on the line segment. This provides a rough estimate of each light's influence on the tile, and because the PDF is positive everywhere, it doesn't introduce sampling bias. The PDF is fast to evaluate, but assumes that tile pixels are roughly evenly distributed between the tile depth bounds, which may not be true. With more accurate PDF, the reservoir quality could be improved, but this simple PDF has been sufficient for us for now. To perform SRS, we divide the lights into 16 separate streams, one for each big tile reservoir slot, and run one sample Arch-Chow weighted reservoir sampling for each stream. This ensures we don't get light duplicates in the reservoir because each slot samples a unique set of lights. We start the stream iteration with the scene light index matching the reservoir slot index. This initial ordering is done to ensure that the first lights are placed in specific slots to optimize performance and to reduce noise in scenes with only few lights. Then in the next SRS iteration, we jump forward to the next group of 16 lights, generate a random offset for the iteration, and offset stream indices with modulo 16 to randomize the streams. This randomization is done to avoid heavyweight lights competing of the same reservoir slot across big tiles and frames. We keep repeating this process until we have iterated through all the lights. To ensure the same random offset sequence for each slot with the pixel shader implementation, we initialize pseudo-random number generator with the seed of the big tile index. At the end of this sampling pass, each big tile reservoir has 16 unique and unbiased light candidates picked based on their approximate influence on the big tile footprint. Here's a code snippet for the big tile slot sampling using SRS based on Arch-Chow WRS. We iterate through the scene lights for a big tile reservoir slot using the described random offset sequence. For each iteration, we evaluate the PDF for each light and use the PDF to probabilistically pick the light. Once completed, we store the light and its weight to the reservoir. Here's a comparison how the big tile SRS reduces noise versus uniform sampling. On the left, we have an image where we pick small tile samples from 16 uniformly sampled scene lights. On the right, we have an image with lights resampled from the big tile reservoir of 16 samples, which has significantly less noise. After the initial big tile light sampling, we resample 1 to 4 lights for small tiles from the big tile reservoirs. These samples will be used for the final lighting evaluation. For the resampling, we will have another round of stratified reservoir sampling to ensure no light duplicates in the small tile reservoirs. This resampling step is independent of the scene's lighting complexity because the resampling is done from the fixed size big tile reservoirs. Each small tile covers 256 pixels, and for the resampling we pick a big tile reservoir based on the location of the small tile center point. However, if we lay out small tile pixels in a regular 16x16 pixel grid, it leads to visible tiling artifacts due to sampling correlation, as shown in the image. To break these tiling artifacts, we interleave the small tile pixels with 4 neighbor tiles over a larger 32x32 pixel footprint. Specifically, we distribute 64 2x2 pixel coarse for each 4 tiles. Here we have the 64 pre-computed coarse sample distributions for the 4 tiles shown in red, green, blue and yellow. For the sample distribution, we use Gaussian Poisson distribution to concentrate a bit more samples to the tile centers while avoiding placing samples from the same tile right next to each other. These sampling patterns are then repeated over the entire rendered image. This interleaved sampling pattern reduces the small tile tiling artifacts. However, we can still see square big tile lighting artifacts because the big tile reservoirs are point sampled at the small tile centers. To fix this, instead of point sampling the big tiles, we use stochastic bilinear filtering between neighboring big tiles. We implement this by randomly offsetting small tile centers when selecting the big tile for resampling. The result is a smoother transition between big tiles and eliminates the tiling artifact. We can still see some interleaved small tiles, but this image is now much better suited for spatiotemporal denoising. For the small tile resampling, we use more refined PDF that better estimates light importance to the tile. We use stochastic PDF evaluation by picking 4 random small tile quartz sample points out of the 64. Then average reflected luminance at the points using light's shadowed illuminance and a PRDF. We calculate the product of standard luminous efficiently weighted light illuminance and PRDF functions for the PDF, which means that materials and lights are assumed to be monochromatic. It would be better to perform weighting after the RGB illuminance and PRDF product so that, for example, red light illuminating a blue surface would result in a lower PDF. But we compromise currently for performance at the expense of some added noise. Here's an example image showing how the shadow term influences noise. If a tile is completely shadowed or all its surface normals point away from the light, we don't pick the light for the lighting evaluation, which reduces noise. Initially we used Lambert PRDF for the PDF, but replaced it with the specular PRDF to reduce specular noise. We found that Lambert plus Pling Fong is a good enough but cheaper approximation for the PDF to reduce the noise of the final Lambert plus GGX PRDF. Also worth noting that we support currently only one lit PRDF, and it might be good to implement different PDF approximations for multiple PRDF to optimize noise. To reduce the ALU usage and VGPR pressure, we also first average luminous efficiency weighted material parameters at the tile sample points and then use the same parameters in reflected luminance calculations of the points. Ideally, our resampling stays unbiased by ensuring the PDF is non-zero everywhere the tile's reflected luminance is non-zero. In practice, we don't fully meet that requirement. For example, it's possible that all the 4 PDF sample points fall in shadow even though some tile pixels are lit. This adds the biased lighting edge noise as shown in the areas highlighted with the red arrows. In the TAA image at the bottom, this biased noise shows as slight darkening in the area. The bias is most obvious in simple lit areas, and to mitigate the issue, we add a small offset to the shadowed cosine term before it's multiplied into the PDF. After denoising, the bias is mostly gone and unnoticeable. For the small tile resampling, we apply the same SRS strategy as in the big tile pass. For the small tile reservoir of n light samples, we split the 16 big tile sample candidates into n independent streams. The resampling cost is independent of n because of the stream splitting. Only the big tile reservoir size and the small tile PDF cost influence the total cost of the pass. Like with the big tile SRS, we start by picking the first n samples from the big tile reservoir for the streams. In this example, we use n equals 4. For the next iteration, we shuffle the next batch of 4 light samples across the streams with a random offset to reduce the likelihood of high importance lights competing of the same reservoir slot for the nearby small tiles. We then repeat this process until all the 16 big tile samples have been processed. At the end of this resampling stage, we have 4 unique high quality light samples that will be used for the final lighting evaluation. The small tile reservoir is exported from the pixel shader to 1 to 4 channel render target using the same 32-bit format as for the big tile reservoirs. It's possible to have more than 4 samples in the reservoir, but we max at 4 for performance and to fit the reservoir into 1 render target. For 1080p, this requires 120 x 68 pixel render target, or from 32 to 128 kilobytes of memory, depending on the reservoir size. Here's a code snippet for the small tile reservoir slot resampling with SRS. We iterate through the big tile reservoir samples for the slot as described. For each iteration, we evaluate the light PDF and calculate the resampling PDF that unbiased the big tile sampling bias. This resampling PDF is then used to probabilistically pick the light. Once completed, we store the light and its weight to the reservoir. After the small tile resampling, we evaluate shadow terms for the light samples. We perform this in a separate pixel shader pass decoupled from the final lighting evaluation. This enables us to evaluate shadows at a lower resolution for better performance. Specifically, we evaluate shadows once per 2x2 pixel small tile quad instead of per pixel. This not only improves shadow evaluation performance by cutting the evaluations to 1/4, but also simplifies the lighting shader. The wave divergence, data access, and VGPR pressure is reduced because the light type specific shadow sampling is kept out of the shader. Since the algorithm is implemented entirely in pixel shaders, shadow terms are stored in 8x8 pixel blocks corresponding to the 64 quad samples of the small tile. This organization reduces wave divergences because of how GPUs generally pack pixel shading to waves. The shadow evaluation code is largely unified for spot and omni-lights, but sunlight uses cascaded shadow maps with a separate path. To reduce memory usage and bandwidth, we use only 8-bit shadow terms and add 1 bit of temporal noise to eliminate banding with TAA. For 1080p, this uses from 0.5 MB to 2 MB of memory. The Deferred shadow pass also enables shadow evaluation to be implemented using different techniques, such as shadow maps or ray tracing, without influencing the final lighting shader performance. Because of our target platforms, currently we use shadow maps for shadow evaluation stored in a persistent, dynamically managed 16 bits per pixel atlas. The atlas contains both spot and omni shadow maps, which are square and power of 2 in size. For spotlights, we use standard projected shadow maps, while for omni-lights, we use octahedral mapped shadow maps. We also resize the shadow maps based on light's distance from the camera to balance the shadow quality with the limited atlas storage. When updating a shadow map for a light, we first render geometry within the light's range to a temp depth buffer and then copy the data into the atlas. For spotlights, we render a regular depth buffer from the light's point of view. Then upon the copy, we linearize and bias the depth values. For omni-lights, we render a cube map to the depth buffer, and during the copy, we map the cube faces to octahedral space in addition to depth linearization and biasing. We also add 2-pixel border upon both copies to support PCF filtering. We support both static and dynamic shadow maps. Static maps are updated only when lights transform or shadow resolution changes. Static maps include only static geometry and are meant for decorative lighting. Dynamic maps are more expensive because they are constantly updated and include both static and dynamic geometry. To avoid performance spikes when many shadow maps require updates, we load balance the updates with a priority queue system to spread the shadow map rendering across multiple frames. For shadow filtering, we use 4-tap hardware PCF with stochastic PCF to produce softer, more natural-looking shadows. This requires only one gather operation from the shadow map per shadow term evaluation. At this stage, we apply also selected IES light profile and angular spot falloff to the shadow term, allowing light-specific shape falloff. We apply IES profiles also during small tile PDF evaluation to reduce noise. We plan to improve shadow quality further with PCSS for contact hardening shadows, screen space Raymar's detail shadows, and ray trace shadows, which can be enabled on higher-end devices. Sharing one shadow term per 2x2 pixel quad works well in most cases, but it can introduce artifacts at object silhouettes where quad pixels should have quite different shadow term values. However, randomized tile sampling and TAA mostly mitigates this issue. While it can still introduce subtle lighting bias at the edges, the artifacts are quite minor. If necessary, we can also fall back to full resolution shadow evaluation to improve the quality at an additional cost. In the lighting evaluation stage, we first fetch small tile light samples and shadow terms for the pixel. Since we want this stage to also run in a pixel shader, we need a way to map screen pixels back to small tile and sample indices. To achieve this, we use a 16x16 pixel inverse LUT that links screen space quad coordinates to the interleaved tile and sample indices. With this information, we can then fetch both the light samples and shadow terms for each pixel. With compute shaders, the inverse mapping isn't necessary, and we could directly evaluate the light samples for the tile pixels and write the lighting result to the lighting buffer with scattered writes. Finally, we accumulate the Lambert plus GGX BRDF contribution for each light sample, weighted by both the sample weight and its shadow term, and write the result to the lighting buffer. Because we store a fixed 1 to 4 light samples per tile, this pass has also fixed cost independent of the scene lighting complexity. The lighting evaluation is also quite unified across all our light types because of the decoupled shadow evaluation, which reduces the divergence with the pixel shader implementation. With compute shaders, we could have coherent lighting evaluation of the tile pixels back to waves, further reducing divergence. To keep the denoising cost low, we are planning to improve temporal anti-aliasing to work as our denoiser and avoid the need for a separate denoising pass, which would consume more bandwidth. However, the main challenge with the standard TAA is the 3x3 pixel neighborhood history color clamping designed to reduce coasting. In our case, this causes flashing lighting splotches shown in the middle, because the pixel neighborhood may not render key lights for a frame, limiting the color range. So we need either to make the color clamping more compatible with the noisy input, find alternative coasting suppression techniques, or provide input data that better suits TAA, or with a combination of these approaches. This is still an active area of R&D for us. For visual results, here is a comparison between 1 and 4 samples per pixel lighting. In the noisy image on the left, the 1 SPP image has more noise as expected. In the TAA image on the right, we can also see that the 4 SPP result is able to reproduce some of the finer lighting details, like sharp specular reflections in detailed geometry. Both converge to quite similar and acceptable results though, without major differences. Here's a visual comparison how big tile reservoir size influences the lighting result. Decreasing the number of big tile samples darkens the scenes, especially in the distance. The darkening is lighting bias caused by capping the light waves to reduce fireflies. Otherwise, increasing the big tile reservoir reduces noise and improves lighting details because the small tile resampling can pull more relevant light samples from a richer set. For the performance profiling, we are using the following hardware setup. It covers one of our weakest Android target phones, a high-end Android phone, and more powerful high-end laptop. Adreno 610 is found in $99 budget phones today and matches roughly Xbox 360 and PS3 for ALU power and memory bandwidth, but runs at 3 watts. Adreno 830 is found in $1,000 phones and matches around 10-year-old consoles and desktop GPUs, but runs at 5 watts. We also use lower rendering resolution on weaker devices. First, we will have an apples-to-apples visual test, comparing our old sun-only lighting with stochastic tile-based lighting. Sun-only lighting simply evaluates shadowed sunlight for every pixel without any kind of light classification. Visually, the sun-only lighting and our STP lighting look almost identical. The main difference is that STP lighting evaluates sun shadows for 2x2 pixel quads instead of pixels, so they appear slightly softer. Our lighting passes evaluate also specular and diffuse IBL, SSA upscaling and so forth, but these numbers include only the direct lighting cost. With 1 SPP stochastic lighting, the cost on the Adreno 610 increased only by 0.66 milliseconds, which is quite modest given it now also handles arbitrary local lights. On Adreno 830 and RTX 4070, the cost increase is around 0.35 milliseconds, but the relative cost increase is higher. These platforms could potentially benefit from compute shader implementations and merging passes to bridge the gap. We also provide how the STP lighting performance scales with the samples per pixel with 50 local lights in the camera FOV, and how it compares to the sun-only lighting performance. The sun-only lighting on the left differs visually, of course, because it renders only the faint directional moonlight. In this scene, the sun-only lighting is a bit more costly, but one SPP adds an extra 1.5 milliseconds on the budget phone and around half a milliseconds on the high-end phone and the laptop. Notably, the small tile SRA pass is now 3 times as expensive as in the previous scene on the budget phone, because it needs to resample from the full big tile reservoirs. An easy way to reduce the cost would be to reduce the big tile reservoir size at the cost of some added noise. 4SPP lighting gets quite expensive on the budget phone, but is more reasonable on the high-end phone and the laptop, especially at those resolutions. The cost of the big tile SRS pass is still tiny, but could be improved to fixed cost with uniform sampling if it becomes an issue with a larger light count. I tested the performance in a separate scene with 500 lights, and the big tile reservoir cost was still only 0.02 milliseconds on all the platforms. We presented a new stochastic lighting algorithm that moved light sampling from per pixel to per tile, drastically cutting bandwidth and divergence and making fully dynamic complex lighting a viable option even on budget mobile phones. The development is still work in progress, but the results are encouraging for both quality and performance that we plan to keep improving in the future. Some of our future work includes implementing compute-shaded variants of the current pixel-shaded passes and profiling on different devices. There are good ALU and bandwidth optimization opportunities that might translate to mobile devices as well. With compute shaders, we could also merge the last 3 passes, small tile resampling, shadows, and lighting, to a single pass, which would give significant performance boost on PC and consoles, and possibly also on some mobile devices. We will also continue to work on TAA to improve denoising and lower the level of noise generated by the lighting algorithm. While the lighting cost remains fixed, the level of noise increases as more lights are illuminating a region. Our biggest challenge currently is to make TAA to work well with the noisy output produced by the lighting algorithm. We are still hopeful that we can denoise the result with modified TAA instead of having to implement a separate spatio-temporal denoising pass. It might be also possible to reduce the noise with previous frame small tile reservoir resampling similar to Rister, but this requires more R&D. The current big tile PDF estimates light's influence on the tile using central line segment between the tile depth bounds. If the depth range is large and the tile pixels are mostly near the near and far planes, lights in the middle of the range are picked too frequently, increasing noise. It would be better to weight the PDF proportionally to the number of pixels at certain depth for higher quality big tile reservoir samples. Another potential improvement is to set the PDF to 0 if spotlight cone doesn't intersect the big tile frustum. The current big tile sampling is very efficient, so we could spend some more cycles to improve the big tile sample quality to better handle a wider range of scenarios. The small tile PDF can also be improved for both performance and quality. Our stochastic PDF evaluation requires currently 4 shadowed illuminance and PRF evaluations, which is rather expensive and results in some bias at the lighting boundaries. We might be able to reduce this to 1 conservative shadow evaluation using tile bounds and hierarchical shadow map, and to have single conservative PRF evaluation by generating a low-res version of the G-buffer. We don't either use any tone mapping in the PDF evaluation, which would also help to bring down the noise. There are also potential low-hanging fruits to improve the quality and performance by tuning the existing algorithm parameters. For example, big tile reservoir size, big tile pixel size, sampling patterns, and so forth can be likely improved. The lighting algorithm supports currently only fully opaque surfaces rendered into the G-buffer. To add support for rasterized semi-transparent surfaces, the light sampling and reservoirs should be extended to volumes that can be efficiently sampled during the rasterization. The algorithm can also be extended to support volumetric lighting, for example by performing small tile resampling upon volumetric gray marching. So that wraps up my presentation, and thank you for listening. I would like to thank Natasha, Sebastian Lagarde, Sebastian Aaltonen, and Jonne Gröndal for reviewing and helping to prepare the presentation, and HypeHype for sponsoring the trip. And finally my wife Laura for her patience and support.